Very good afternoon to everyone. This is Shubhangi Rao and I am working as an assistant professor at MLR Institute of Technology, and I am teaching this subject electromagnetic field to second year EEE students. In today's class, today's lecture, we are going to discuss about Maxwell's first equation and Poisson's and Laplace equation. These two derivations are very important for exam point of view. So, let's start with Maxwell's first equation. So, this Maxwell's first equation, we have used already few formulas. By using those formula only, we have to derive Maxwell's first equation. So, let's start. We know that the divergence of electric field, electric flux density is given by this formula. Divergence of D is equals to integration of D dot ds, and we are putting the limit of del V tends to 0. So, here we are writing divided by del V, and also we know this formula, del dx by del x plus del dy by del y plus del dz by del z. According to Gauss law, we already know xi is equals to q, which is equals to integration of surface integration of d dot ds. So, expressing this Gauss law per unit volume basis, we get q upon del V is equals to integration, surface integration of d dot ds upon del V. Now, let us consider that this limit del V tends to 0. So, volume shrinks to 0. So, here we get a new formula, limit del V is equals to 0, q upon del V is equals to limit of del V tends to 0 integration of d dot ds upon del V. But as we know, limit del V is equals to 0, q upon del V is equals to rho V at that point. So, if you notice, this equation 5 gives the volume charge density at the point where divergence is obtained. This is a very important point. This equation 5 is giving the volume charge density rho V at the point where divergence is obtained. Now, if you equate this fifth equation and this first equation, what we get? Divergence of D is equals to rho V. Once again, I will go back to the first slide. We have first equation, divergence of D is equals to integration of d dot ds upon del V, where the limit is del V tends to 0, and here we have got the same, okay, rho V. So, we can just equate it and we can write divergence of D is equals to rho V, which is generally written in this format, del dot D is equals to rho V, and this is the volume charge density around a point, and this equation is called Maxwell's first equation applied to electrostatics. This is also called the point form of Gauss law, or you can call it Gauss law in differential form. So, this was Maxwell's first equation. I hope it's clear. Next derivation for today is Poisson's and Laplace equation. Okay, again already used formulas we are going to use here to derive Poisson's and Laplace equation. Just now we have seen from the Gauss law in the point form, or which is also called differential form of Gauss law, we have this formula, divergence of D is equals to rho V, where D is the flux density, rho V is volume charge density. Also, we know that for a homogeneous, isotropic and linear medium, the flux density and field intensity are directly proportional. So, by that we get the formula D is equals to epsilon E. So, here now in this formula we can put epsilon E in place of D. So, this formula becomes del dot epsilon E is equals to rho V. Also, from the gradient relationship we know E is equals to minus del V. Negative gradient of voltage is equals to electric field. So, now if you substitute this fourth into third in place of E, if we put this new formula, we get del dot epsilon minus del V is equals to rho V. Then we rearrange it, we simplify it, and we get the formula minus epsilon del dot del V is equals to rho V. Again you simplify it, you get this epsilon here into the denominator, we get del dot del V is equals to minus of rho V upon epsilon. And this del dot del is called del squared, or it is also called Laplacian. Okay, del square is called Laplacian. So here it became Laplacian of V, which is equals to minus rho V upon epsilon. This equation is called Poisson's equation. Right. Now from this equation itself we will get Laplace equation also. If in a certain region the volume charge density means rho V becomes 0, which is true actually for dielectric medium, then we get the Poisson's equation. So when you put rho V is equals to 0 in this equation, we get Laplace equation del square V is equals to 0, right? So you can call it the special case of Poisson's equation, and it is called as Laplace equation. As I already told, this del square is called Laplacian. Okay. There are one or two key points which we can take from this. If rho V is equals to 0, still in that region point charge, line charge or surface charge may exist at singular location. Another point, the equation number 7 is for homogeneous medium for which epsilon is constant. But if epsilon is not constant and the medium is inhomogeneous, then equation number 5 means this one. Equation number 5 should be the Poisson's equation for inhomogeneous medium. So equation number 7 is the Poisson's equation for homogeneous equation, and equation number 5 is the Poisson's equation for non-homogeneous medium. So this was Poisson's and Laplace equation. So in this lecture we discussed about this Poisson's and Laplace equation and Maxwell's first equation. I hope it is clear to everyone. In case of any doubt, you can please write to us. Thank you very much.